degree of retardance. Reaction is equal to 1, this one reaction. Then degree of freedom is equal to 3 minus 1 is equal to 2. Reaction is equal to 2. Then degree of freedom is equal to 3 minus 2 is equal to 1. 1, 2, 3. If reaction is equal to 3, then degree of freedom is equal to 3 minus 3 is equal to 0. Restrictions clamped. Degree of restriction, DOR is equal to degree of restriction. Opposite to it is degree of freedom. U semicolon du by dx is equal to gradient means slope is equal to theta is equal to rotational displacement m minus 1 d square u by dt square plus du by dt plus u is equal to F, which is dynamic force. M d square u by dt square is equal to inertial force, maybe resonant force or natural frequency. M by I is equal to F by Y is equal to E by R. U is directly proportional to F. M d square u by dt square plus du by dt plus u is directly proportional to F. If u raised to 0 is equal to 1, du by dx is equal to theta, d square u by dx square is equal to m over ei is equal to 1 over r. D cube u by dx cube is equal to shear force SF. d4 u by ds4 is equal to reaction force F or F reaction force. Sigma, this one is the graph. Sigma is directly proportional to epsilon. This is P, this is delta. P is directly proportional to delta. Newton's method, dA Lambach's method, ds is equal to 3 minus 3 which is equal to 0. E nu is equal to 0. Summation h is equal to 0. Summation m is equal to 0. Here summation u is equal to 0. Then here 1, here 2. ds is equal to 2 minus 3 is equal to minus 1. 1, 2, 3. ds is equal to 3 minus 3 is equal to 0. Then here 1, 2, 3, 4, 5, 6. ds is equal to 6 minus 3 is equal to 3. ds is equal to 4 minus 3 is equal to 1. Remove the couple implies pin joint. This. ds is equal to 5 minus 3 is equal to 2. Here 1, 2, 3. dk is equal to 3 is equal to 2j minus E. In the beams, E is equal to reaction plus inextensible condition. dk is equal to 3j minus E, which is in frames. Here in this dk 1, 2, 3. dk is equal to 3. Here dk is equal to 2. Here dk is equal to 0. Here it is theta naught, theta 1 force, first force on theta naught, then second force on theta 1, third force on theta 2, fourth force on theta 3, then fifth force as given, then dk is equal to 5. Here the forces are, here for example upward force 1, 2, 3, 4. Maybe there is no upward force here, it may be by mistake. A, B, here dk is equal to 4, ds is equal to 4 minus 3 is equal to 1. Here for example, here is the curve, here is the curve, here is the curve, here it is 90 degree. In this, here it is theta 1, theta 2, theta 3. This one is a fixed. These are the forces 1, 2. ds is equal to, ds is reaction, 6 is reaction, 3 is the equilibrium. ds is equal to reaction minus number of equilibrium condition. where number of equilibrium condition is 3 d. Then here for example here is the 4 theta 1 2 3 4 5, then here 6 here, then here ds is equal to 3, dk is equal to 3 or 4, axial rigidity which is AE, torsion rigidity which is CJ or GJ, T over J is equal to J theta by L is equal to tau by R, T is equal to GJ theta, then T is equal to T maybe is the torsion force is equal to J theta by L, GJ theta by L. Here is the case of dam. It is length A. Here it is the up to the level which is water. Here it is weight W. Here it is breadth B. Here it is reaction. Here it is force. Here it is H. This one is tau. For example, then here form is the diagram. For example, the slanting like that. Here are the upward arrows sigma. Here are the downward arrows, stability of imaginary section, the tension at the base section, overturning over the heel, sliding along the base, crushing of masonry at the base. Condition 1. The condition to avoid tension in the masonry at the base, sigma is equal to W by A axial stress plus minus My by I bending stress. Sigma maximum is equal to W by BD into 1 plus 6C by D. Small capital M is equal to W into E. I is equal to BDQ by 12. Y is equal to D by 2. Sigma minimum is equal to W by BD into 1 minus 6C by D. No tension develops where sigma greater than equals to 0. Then if put 0, then 0 is equal to W by BD. Then which is equals to 1 plus 6C by D. Then E is equal to D by 6 or negative or D by 6. The limiting eccentricity can be equal to D by 6 of either side of geometrical axis of the base section. Thus resultant must lie within the middle third of the base within order to avoid tension. The condition to prevent overturning: the masonry will tend to overturn about B, and the overturning moment is due to the lateral pressure P and P into H by 3. This is RA, this is RB, here is like this is the downward force. These are the downward forces. Before proceeding to the dams further, firstly learn the basics, which is shear force and bending moment. Hey, this is cantilever beam, this is simply supported beam, this is overhanging beam, fixed beam, this is fixed beam in which both ends are fixed or built-in walls. In continuous beam, this is continuous beam. For example, this one is continuous beam. This is concentric or point load. This is concentrated or point load. This is uniformly distributed load. This is uniformly varying load. This is shear force and bending moment diagram for a cantilever beam. For example, here is the length L, it is weight W, it is X, then this is X, A, this one is W plus W, here it is W into X, it is bending moment diagram, here it is negative, here it is W into L. How these forces are made? For example, here if Fx is applied, Fx is equal to plus W, Fx is equal to plus W. Mx, because Fx is equal to plus W, because here the force is in clockwise direction. That's why Mx is equal to plus W. Here the Mx is equal to minus W into X. Maybe take a section X at a distance X from the free end. Consider the right portion of the section. Here is a cantilever beam of length 2 meter, carries the point load as shown in the figure. Draw the shear force and bending moment diagram for cantilever beam. For example, here is 300 Newton, 500 Newton, 600 Newton, 0.5 meter, 0.7 meter, 0.8 meter. Here are the shear forces. FD is equal to plus 800 Newton, FC is equal to plus 800 plus 500 is equal to plus 1300 Newton. Shear force at B, FB is equal to plus 800 plus 500 plus 300 is equal to 16,000 Newton. FA is equal to 1600 Newton. Then here is the 800 Newton force, this is 500 Newton force, this is 300 Newton force, this is positive, this is negative. Then here is the bending moment at any section between C and D at a distance X, and D is given by Mx is equal to minus 800 into X, which follows a straight line. MC is equal to minus 800 into 0.8 is equal to minus 640 Newton meter. For example, here it is the 640 Newton meter. This is the baseline. Then the bending moment at any section between B and C at a distance X from D. At a distance X from D is given by Mx is equal to minus 800x minus 500 into X minus 0.8. Then here bending moment at B is obtained by substituting X is 1.5 meter in equation first. MB is equal to minus 800 into 1.5 in minus 500 into 1.5 minus 0.8, which is equal to minus 1550 Newton meter, which is 1550 Newton meter B dash. MA is equal to minus 800 into 2 minus 500 into 2 minus 0.8 minus 300 into 2 minus 1.5, which is equal to minus 2350 Newton meter. So here is 2350 Newton meter. This is one is the which diagram? Bending moment diagram. This one is shear force and bending moment diagram for a cantilever beam with a uniformly distributed load. Here it is W per unit length, X, X, L, B. Then here it is W into X, which is positive, bending, which is shear force diagram. Then here it is W minus W X square by 2. Here it is W into L square by 2. Here a cantilever beam of length 2 meter carries a uniformly distributed load of 1 kN per meter run over a length of 1.5 meter from the free end. Here it is 1.5 meter. So here Fx is equal to, if consider a section between C and B, then between C and B, Fx is equal to plus W into X, which is equal to 1 into X. At B, X is equal to 0, hence Fx is equal to 0. At C, X is 1.5, hence Fx is equal to 1 into 1.5 is equal to 1.5 kilonewton. The shear force follows a straight line law between C and B. Listen, here FB is equal to 0, FC is equal to 1.5 kilonewton, and FA is equal to SC is equal to 1.5 kilonewton. The bending moment at any section between C and B at a distance x from the free end B is given by mx is equal to minus w into x by 2 is equal to minus 1 into x square by 2 is equal to minus x square by 2, where W is equal to 1 kilonewton per meter. At B, x is equal to 0, MB is equal to minus 0 square by 2 is equal to 0. At C, x is equal to 1.5, MC is equal to minus 1.5 square by 2 is equal to minus 1.125 Newton meter. Bending moment at any section between A and C at a distance x from the free end B is obtained as total load due to UDL is equal to W into 1.5 is equal to 1.5 kilonewton. The load is acting at a distance of 1.5 by 2 is equal to 0.75 meter from the free end B, or at a distance of x minus 0.75 from any section between A and C. Here mx is equal to minus 1.5 into x minus 0.75, mc is equal to minus 1.5 into 1.5 into minus 0.75, which is equal to minus 1.125 Newton meter. ma is equal to minus 1.5 into 2 minus 0.75 is equal to minus 1.875 Newton meter. Now the bending moment diagram is drawn as shown in figure 6.17c. In this diagram, cc dash and cc dash is equal to 1.25 Newton meter and a dash is equal to 1.875 Newton meter. The points B and C on a parabolic curve, whereas the points A dash and C dash are joined by a straight line. Listen, this is parabolic, this is straight line. It is W into x by L. It is W x square by 2L, parabolic curve. This one is a shear force and bending moment diagram for a cantilever carrying a gradually varying load. Maybe here it is the bending moment diagram. Here it is the baseline. Here it is the W into x cube by 6L. Here it is W L square by 6. Here the equations. In this, the shear force and the at the section x at distance x from phi and is given by fx is equal to x into wx by L by 2, which is here it is x wx by L. Here it is wx square by 2L. At B, x is equal to 0, fb is equal to w into 0 square by 2L is equal to 0. At A, x is equal to L, hence fa is equal to wl square by 2L is equal to wl by 2. mx is equal to minus wx square by 2L into x by 3 into x by 3, which is equal to minus wx cube by 6L. Here the wx square by 2L is the area of triangle BCX. It can be the area of the triangle BCX. Okay, here BCX. For example, here, not for example, sorry, it is wx square by 2L into x by 3. X by 3 is the centroid of the triangle. For example, here this with distance of center of gravity of the triangle from x. Distance of the center of gravity of the triangle from x, which is x by 3. Then by multiplying minus wx square by 2L into x by 3, one can get minus wx cube by 6l, which is mx. Now the shear force and bending moment diagrams for a simply supported beam with a point load at midpoint. Here for example, here it is W, here then here the reaction W by 2, dividing the reactions. Why the reactions here are for W by 2? Okay. Now consider any section between C and B at distance x from the end A. The resultant force on the left portion will be equal to W by 2 minus W is equal to minus W by 2. This force will remain constant between C and B, hence the shear force between C and B is equal to minus W by 2 . Then bending moment diagram. At the section C, the shear force changes from plus W by 2 to minus W by 2. The shear force diagram is shown in figure 6.24b. The bending moment at any section between A and C at a distance of x from the end A is equal to then mx is equal to Ra into x, or mx is equal to plus W by 2 into x. Here ma is equal to W by 2 into 0, which is equal to 0 at x is equal to L by 2. MC is equal to W by 2 into L by 2 is equal to WL by 4. Mx is equal to Ra into x minus W into x minus L by 2, which is equal to W into x by 2 minus Wx plus W into L by 2, which is equal to WL by 2 minus 2x by 2. At C, MC is equal to WL by 2 minus W by 2 into L by 2 is equal to W into L by 4. At B, x is equal to L, MB is equal to WL by 2 minus W into L by 2, which is equal to 0. MA here as given W by 2 into 0 is equal to 0. MC is equal to W by 2 into L by 2 is equal to W into L by 4. Now shear force and bending moment diagrams for a simply supported beam with an eccentric point load. Here it is W, here it is small x, here it is capital X, it is A, it is B, it is length, this is RA, this is RB, this is W into B by L, this is W into A by L, this is W, this is shear force diagram, this is bending moment diagram is W into AB by L. Here RB into length L is equal to W into A, then RB is equal to W into A by L. RA is equal to W minus RB, which is equal to W minus W into A by L, which is equal to W into 1 minus A by L, which is equal to W into L minus A by L, which is equal to W into B by L. Fx is equal to plus Ra is equal to W into B by L. Then now considering any section between C and B at a distance x from the end A, this is one is the diagram. the resultant force on left portion will be Ra minus W, which is equal to W into B by L, minus W is equal to W into B minus L by L, is equal to minus W into L minus B by L, is equal to minus W into A by L, which is minus W into A by L. Bending moment at any section between A and C at a distance x from the free end A is given by mx is equal to Ra into x is equal to plus W into B by L into x. At A, x is equal to 0, then MA is equal to W into B by L into 0 is equal to 0. At C, x is equal to A, then MC is equal to MW into B by L into A is equal to W into A into B by L. Note, by applying the common sense also, we can solve the questions. Like in this problem. Shear force and bending moment diagrams for simply supported beam carrying a uniformly distributed load. Here it is Ra, it is Rb, this is small x, this is capital X, W per unit length. Here Ra is equal to reaction at A and Rb is equal to reaction at B. Ra is equal to W into L by 2 Fx is equal to plus Ra minus W into X. Consider at any section X, capital X, at distance small x from the left hand A, the shear force at a section Fx is given by Fx is equal to Ra minus W into X is equal to plus W L by 2 minus W into X. From the equation it is clear that shear force varies according to straight line law. The values of shear force at different points are Fa is equal to plus W L by 2 minus W into 0 by 2 is equal to plus W L by 2. Fb is equal to W into L by 2 minus W into L, which is equal to minus W L by 2. At C, x is equal to L by 2. Here Fc is equal to W into L by 2 minus W into L by 2, which is equal to 0. Then we get this diagram. This is shear force diagram. If, for example, if the bending moment at the section capital X at a distance small x from the left hand A is given by mx is equal to plus Ra into x minus W into x by 2, then Ra is equal to W into L by 2 into x minus W x square by 2. From the equation second, it is clear that bending moment varies according to the parabolic law. Ra into x minus W into x by 2. Here it is, for example,